Okay, let's talk about relativity and frames of reference. So this is going to be section 6.1 and 6.2. And basically, what is a frame of reference? What's relativity? And basically, a frame of reference is a coordinate system which an observer makes measurements. So, I mean, the classic one I always give, and we'll be doing this in relative velocity, is if you have a tree here, and if I'm walking towards the tree, now 2 meters per second, and somebody's on a bicycle cycling towards a tree, and I don't know, they're doing 5 meters per second, the tree relative to the ground, me, and the cyclist are all doing different speeds, and we all see different things. I see, standing here, I see that I'm moving towards the tree, and a cyclist is approaching me. The cyclist sees that they're approaching the tree and me. The tree sees the cyclist and myself moving towards them. So we've got 3 frames of reference here. We can look at the frame of reference of the tree and see what's happening, frame of the reference of me walking, or the frame of reference of the cyclist. So a frame of reference is basically an observer. What's the observer actually seeing? Okay, so we're also going to talk about inertial frames of reference. We try and do everything, if we can, in an inertial frame of reference. There are also non-inertial, which we'll discuss shortly. But the thing about an inertial frame is it has constant velocity. So if I'm walking towards the tree at 2 meters per second, I'm not accelerating, so therefore that's an inertial frame. If that cyclist is doing 5 meters per second, that's also an inertial frame. Now that tree is not moving anywhere, it's not accelerating, so that's also an inertial frame. So basically constant velocity means no acceleration. And that's the big thing. If there is no acceleration, then it's an inertial frame. If there is any acceleration going on, then we have to take things and take into account relativity and to other terms, which we will do in the rest of the section. Okay, and the other thing is the Newton's laws of motion and gravity, acceleration and gravity still work, are valid. So that would be an inertial frame. So we can also take a Galilean principle, which Galileo first proposed, which is basically the laws of mechanics are the same in all inertial frames of reference. And we haven't found that to be wrong. So in theory, if we do have an inertial frame in Hamilton, and we do an experiment there, I drop something, and if I have an inertial frame in Paris and I drop something, then we should get the same result. Let's just try and do an example. Example 6.1, which is in the notes, and what that says, motion of ball dropped in a van travelling at constant speed. So draw a picture. We have a van. And if that van is travelling at a constant speed or velocity, basically what happens here, if I drop the ball, I have a ball and I drop it, this is me in red, what I see is the ball drop, dun, 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 straight down. But because the van is moving, if you have somebody here, what they see is the ball as it drops. Because the van is moving, they see the ball do that. Because that's a different observer, they're in a different frame of reference than me. I look at it and see a ball just dropping straight down. This person sees a ball arcing in a perfect parabola. But in both cases, the laws, Newton's laws, are held true. invalid. So this ball has the same mass and energy for both observers. So let's do relative velocity. I was already doing a bit with that example with the tree. So let's talk about, let's do this example again. So I've got my tree and I'm doing 2 meters per second, and the cyclist is doing 5 meters per second. Now, question is, we're going to say that Earth is that tree is on the ground. So what we're going to call that is, we'll call that a ground system. How fast am I going towards the tree? Well, if the tree's got zero velocity, so velocity between, me and tree equals 2 meters per second. How about for the velocity between the cyclist? The cyclist and the tree is going to equal 5 meters per second. But how fast is the cyclist going relative to me? So velocity, cyclist, me, it's going to be 5 meters per second minus the 2 meters per second is equal to, so the cyclist is going 3 meters a second faster than I am. Hopefully you can see this from your own personal experience. And this is actually quite important. I mean, I don't know if anybody remembers Scott Dixon. He used to race IndyCar, he probably still does race Indy cars over in Indianapolis 500, and they'll do speeds like 350 kilometers per hour. So they've got a racetrack, they're in their cars, there's Scott, boom, it's crash helmet, there's another car, and somebody was saying, do you know how fast you're going? Because they're doing 350 kilometers per hour plus. He says, no, I mean, all you're doing, you don't know how fast you're going until you hit the wall. Because he's comparing his speed to this driver. So Scott might be just doing 2 kilometers per hour faster than that one, 351. But compared to the wall, both those cars are going really fast. Compared to each other, they're just sort of doing this. Compared to the wall, they're going push. So anyway, let's try a couple of examples. So let's actually set this up formally. This is section 6.2. So we're going to set up velocity of the object relative to the ground. So we're going to set up some terms. VOG, object, ground. Okay, velocity, object, moving system. What's that? Yeah. Moving, object, moving, and velocity, what's that one? SG, moving ground, which is basically just a very complicated way of saying what I was saying here. So let's try 6.1. And we can work out for the standard Galilean transform, the velocity of the observer relative to the ground. So if I'm on the back of a truck, so this is me on a truck, this is S, the moving system. This is, the tree is going to represent the ground, and I'm going to be the object. So I drop a ball or something like that. So, or I'm walking forward. So if I'm walking forward on a train or something like that. So what this is the velocity of me relative to the ground is going to equal the velocity of the train or the truck or whatever relative to the ground plus whatever speed I'm walking forward plus the object. So what this is if I'm on a train, the train's moving forward, my total velocity towards that tree is equal to my velocity relative to the train plus how fast is that train going. So I add my speed to the train speed, boom, that gives you total speed. For some reason we love trains when we're doing these examples. Okay, so let's try exercise 6.1. Okay, a van moves at 3 meters per second due east. So we've got a van. It's doing 3 meters per second east. Remember, north, south, east, west. And there's a stationary observer, so over here, relative to that. And somebody rolls a ball along the floor of that at 2 meters per second. How fast is the ball going relative to me? So in this case, we can say velocity of the object to the ground is equal to the velocity of this of the van plus the ground plus the velocity of the ball relative to the van, which is going to equal, well, the van's doing 3 meters per second and the ball relative to the van is doing 2 meters per second, so equals 5 meters per second. So that ball is actually headed towards me at 5 meters per second. Isn't that cool? Okay, but what happens if the person rolls the ball the other way? So we've got, let's do 6.2. So we've got the same thing. We've got a van. We've got me. I'm not going anywhere, so I'll put an earth sign in. And so the van's doing now the van's doing 2 meters per second. And somebody rolls that ball backwards at 2 meters per second. How fast is that? How fast is that actually going, that ball travelling relative to me? So again we go VOG, the velocity of the object, in this case of the ball, relative to me, equals the velocity of the van relative to me plus the velocity of the object relative to me. Now what we have to take into account here is the van. So I'm going to set this up. This is going to be positive. Positive is going to be that way and up. So the van is headed towards me at 2 meters per second. Plus, and then I add on the speed of the ball, but the ball's going the other way. So that's going to be plus negative 2 meters per second because that ball is going that way. So the actual velocity of the object, of the ball relative to me, is 0 meters per second. 2 plus negative 2 is 0. So if I was on a train, for example, or if I was standing here, the ball would appear not to move. Everything else would, but the ball would appear to be in the same spot. Okay, what about now? Let's take a harder example. Example 6.3. I probably should have done this before I worked this through. Repeat the example. So we've now got the van. I'm going to do a top view of the van. This is the top view. And the van is moving 3 meters per second that way. Due east, and the ball is rolled 2 meters per second to the side of the van. 2 meters per second that way. And if this is me standing here, I'm the observer, how fast is it going now? And it's the same thing. VOG equals VSG plus VOS. Let's just remind ourselves what this means. The velocity of the object, the ball, relative to me, is equal to the velocity of the van, the moving system, the van, relative to me, plus the velocity of the object relative to me. So how do we do this? And the thing you have to remember in this case is velocity is a vector. So what we actually have is we add them up. We go 3 meters per second. Remember, use the dog greeting method of adding vectors. 2 meters per second These are set up at right angles. The resultant ball is actually going to travel that velocity relative to me. So to find out the magnitude, so how do we work out the magnitude? We use Pythagoras. VOG equals root of 3 squared plus 2 squared equals root 13, which is equal to root 13 equals 3.606 meters per second. So the ball's travelling 3.606 meters per second, and then we have to find out the angle, which in this case we're going to use tan theta equals tan inverse of opposite over adjacent, which equals tan inverse of 3 over 2, 3 meters per second over 2 meters per second equals tan inverse tan inverse, come on Claire, tan inverse 1.5 equals 56, okay, wrong way around, 2 meters, opposite is 2, 3, that looks better. Tan inverse of 0.6666 equals 33.69 degrees. So that angle in there is 36.69 degrees. We don't know if it's going that way or that way, but we know it's going to pass me on one side or the other. So remember, velocity is a vector, so we'd still add them just like any other vector.